This video provides an overview of the functionality of CSection. CSection is a numerical tool devoted to the computation of the mechanical characteristics of any homogeneous or composite section. To start, what are the sections that can be computed by CSection? Here are some examples of homogeneous and composite sections. The shape of the section may be compact or walled, thin or thick, open or closed, symmetric or not. The section is homogeneous or composite. Each material can be anisotropic and free-oriented. Winding is also possible. The framework is then very large and many engineering applications may be concerned. For the composite case, this ranges from the aircraft to the automotive industry, the sport equipment, and even the reinforcement in civil construction. For the homogeneous case, thin and thick walled sections will especially find a real added value in terms of results. For a given section, defined by its geometry and its materials, CSection computes systematically all the mechanical characteristics of the section, denoted here by MCS. These characteristics, which go far beyond the usual or conventional ones, constitute a set of information that help understand the section mechanics and predict the beam behavior that will result. That's why CSection can be used to help section design, shape and materials. From a computational point of view, CSection is developed on Matlab platform and can be used as a Matlab tool. It runs on a common PC and the time to compute a section is about a few seconds. Its graphical user interface is designed to be easily used by any engineer or technician. Besides, using CSection doesn't require particular theoretical or numerical knowledge. Now, let's specify what are exactly the sectional characteristics computed by CSection. To do so, we have first to fix some notations and record some results. Z being the beam axis and X and Y the sectional axis. The classical cross-sectional 1D quantities are U and omega for the translation and the rotation of the section, and gamma and chi, the correspondent sectional strains. The cross-sectional stresses, also called the internal forces, are the shear forces Tx and Ty, the axial force N, the bending moments Mx and My, and the torsional moment Mt. These cross-sectional stresses and strains are related by the 1D constitutive law that can be expressed by the following 6-6 matrix. This matrix is here the stiffness matrix. For the case of homogeneous and isotropic section that is symmetric with respect to X and Y axis, this matrix would be diagonal. However, for an arbitrary composite section, this matrix may be a full matrix. In that case, each of diagonal component expresses a kind of elastic coupling. For example, the 4-6 component is related to the coupling between the torsion and the bending with respect to X. What is important here is that this matrix depends only on the section nature, shape and materials. So we can say that this matrix is then a sectional characteristic. Besides, for a beam, we recall that far from the ends, the 3D stress field is given by the 3D Saint-Venant solution. An important property of this 3D Saint-Venant stress field is that it is a linear combination of the 6 internal forces and stress type fields, so that it corresponds to each unit internal force a stress type field, here in blue color. It is shown that these stress type fields are independent from the loading and depend only on the section nature. These 6 stress type fields or sectional stress fields are then also sectional characteristics. To sum up, the sectional characteristics that have been identified are the 6-6 matrix of the 1D constitutive law and the stress-type fields related to each one of the 6 internal forces. It is worth noting that the knowledge of this matrix allows deduce all the usual or conventional sectional quantities as the position of the inertia center, the orientation of the inertia axis, the position of the shear center, the different rigidities related to tension, bending or torsion, the elastic coupling constants, and many other useful constants. Regarding the sectional stress fields, it's worth knowing that the stress components in the plane of the section, those in red color, are 0 for the homogeneous and isotropic case. However, for the anisotropic and composite case, these components are not necessarily null and would have the same magnitude than the other stress components. This last point is fundamental for a composite section with anisotropic phases when it comes to evaluate the strength of each material. Now, how are these sectional characteristics determined by C-section? To identify these sectional characteristics, C-section refers to the 3D Saint-Venant solution. For beams, Saint-Venant solution is that famous solution that describes the 3D exact solution in the interior zone of the beam far from the ends. The Saint-Venant solution we talk about here is not the original one established for homogeneous and isotropic beam and due to Saint-Venant, but that one extended to composite section and uniform lateral loading, which is due to Eisen. Because it describes the exact 3D solution in the interior zone of the beam, Saint-Venant solution reflects the real behavior of the section that results from its shape and its material. From a mathematical point of view, it is shown that it is possible to extract from the computation of 3D Saint-Venant solution several mechanical characteristics that depend only on the section nature, shape and materials. The sectional 6-6 matrix and the sectional stress type we have seen previously are part of these sectional characteristics. An important property of these sectional characteristics is that they can be deduced from the resolution of a set of 2D elastic problems defined only on the section. For a given section, defined by its 2D geometry and its materials, C-section solves systematically this set of 2D problems and deduces all the sectional characteristics. It is worth noting that the computations are performed by 2D finite element method, free from all the classical beam assumptions. About these assumptions, we recall that in Saint-Venant solution, the section is naturally free to warp or deform in its plane and out of its plane, so that it's also possible to extract from Saint-Venant solution the Poisson's effect and the out-of-plane warpings associated to each one of the 6 internal forces. These sectional deformation modes are also sectional characteristics. So, to summarize, the sectional characteristics that can be extracted from 3D Saint-Venant solution and computed by C-section are the 6-6 matrix of the 1D constitutive law, the sectional stress type fields, and the sectional deformation modes. For any given section, defined by its geometry and its material, C-section computes its characteristics systematically by 2D FEM, free from all the conventional beam assumptions. As application of C-section, the rest of this video presents the results obtained for 2 cases of section: homogeneous section and a composite section. The first section is homogeneous and isotropic. Its shape is a thick U. On the left side, one can show the geometry and the mesh of the section, the inertia axis, the position of the section center, and also the position of the shear center. The table on the right side gives the numerical values of the usual sectional constants, and the table below specifies the 6-6 stiffness matrix of the 1D constitutive law. This section being symmetrical only with respect to y, the matrix indicates, as expected, a coupling between the shear force Tx and the torsional moment Mt. This slide gives as examples a few sectional stress type fields. On the left, the sectional axial stress field sigma zz related to the bending moment with respect to x. In the middle, the shear due to the shear force Ty, and on the right, the shear due to the torsional moment. It is of course possible to display for each internal force the sectional stress field for each one of the 6 components of the stress tensor. But let's move on to the sectional deformations. This slide shows on the top the Poisson's effects related to the axial force and the bending moments, and on the bottom the out-of-plane warpings due to the shear forces and the torsional moment. To sum up for this homogeneous section, all the sectional characteristics have been computed. The 6-6 matrix of the 1D constitutive law, the usual constants, the sectional stress fields, and the sectional deformation modes. Let's discover now the case of the composite section. It's a laminated and symmetric section. The layers have the same thickness and are constituted by the same transversely isotropic material. The table on the right gives the usual constants, and the one below gives the 6-6 stiffness matrix. As expected, this laminated presents only 2 types of elastic coupling. The 4-6 component is related to the bending torsion coupling, and the 1-3 component is related to the tension bending coupling. We will now move on to the sectional stress field. Note first that for the composite case, the stresses are displayed by material or by subdomain. Thus, right to an interface, the stress fields will be continuous for certain components and discontinuous for others. That, of course, according to the orientation of the interface. Here are the axial stresses associated to the axial force and the bending moments. These stresses are naturally discontinuous right to the interfaces. The 2 figures below are related to the shear force Ty, for which we give the distribution of the shear stresses sigma yz and the axial stresses sigma zz. Note that, as expected, the shears appear continuous right to the interfaces and vanish at the ends. This result on the shears for a laminated section is witnessing the quality of the results provided by CSection. Note also that unlike the case of homogeneous and isotropic section, the shear force Ty generates non-zero axial stresses for this composite section. At last, it is shown at the bottom right the distribution of the shear associated to the torsional moment. It's of course possible to display for each one of the 6 internal forces the sectional stress field for each one of the 6 components of the stress tensor. But let's move on to the sectional deformation. This slide shows that, unlike the homogeneous and isotropic case, all the internal forces contribute to the Poisson's effects and to the out-of-plane warpings. Note here the complexity of the sectional deformation for this composite case. That's all for this section. In conclusion, Keep in mind that for any homogeneous or composite section, C-section provides systematically all its mechanical characteristics. This is performed by 2D finite element method, free from all the classical beam assumptions. These sectional characteristics can help understand the mechanics of the section and predict the beam behavior this section can generate. That's why C-section can help section design, shape and materials. From a computational point of view, C-section is developed on Matlab platform and runs as a Matlab tool. On a common PC, the complete treatment of a section needs usually a few seconds. Besides, the C-section graphical interface is designed to be immediately and easily used by an engineer or a technician. Finally, we must emphasize that using C-section doesn't require particular theoretical or numerical knowledge, apart from the usual knowledge on sections and beams. This ends the overview of C-section.